What if I told you that right now something is leaving our solar system that might completely change everything we thought we knew about our place in the universe? And what if I told you that for 8 critical days this object performed some kind of maneuver behind the sun where we couldn't see it? Look, I know how that sounds, I really do, but stick with me here because what happened with this comet, and I'm using the word comet very loosely, is genuinely bizarre. And I'm not talking about internet conspiracy theory bizarre, I'm talking about peer-reviewed, published scientific papers, multiple international observatories, PhD astrophysicists scratching their heads kind of bizarre. So let's talk about C/2023 A3, which everyone's been calling Tsuchinshan-ATLAS, or just 3I Atlas for short, because this thing just did something behind the sun that has some very smart people asking very uncomfortable questions. October 29th, 2025, 7:47 a.m. Eastern Time, this interstellar comet reached perihelion. That's its closest approach to our star. It came within 203 million kilometers of the sun's surface. Now, for the first time in 10 billion years, and yes, you heard that right, 10 billion years, this object felt the warmth of another star system's furnace, and then it went silent. For 8 days, 3I Atlas was positioned directly behind the sun from our perspective. Every telescope on Earth, blind, our most powerful space-based observatories, useless. This Manhattan-sized visitor from beyond our solar system performed whatever it was going to do in complete privacy. But here's the thing that should make your spine tingle a little bit. During those final hours before it disappeared behind the sun, something changed. The comet began brightening rapidly, and I don't mean normal comet brightening, I mean its glow was intensifying at a rate that far exceeds anything we've ever observed from any natural comet in history. And the color, oh man, the color, it turned bluer than the sun itself. Let that sink in for a second. This object's surface should be freezing. We're talking hundreds of degrees colder than our star, yet somehow, impossibly, it's emitting light with a color temperature that's hotter than the photosphere of the sun. That's not how this is supposed to work. That's not how any of this is supposed to work. Now, today, well, October 30th, when it emerged, the Punch satellite constellation captured the first images of 3I Atlas coming out from behind that solar glare. And according to NASA's automatic tracking systems, the comet maintained its expected trajectory, no deviation, no sudden course correction, no using the sun's gravity to redirect toward Earth. At least that's what the public data shows. But there are gaps, significant gaps in the story. NASA allegedly has high-resolution images from the Mars Reconnaissance Orbiter taken when 3I Atlas passed within 30 million kilometers of Mars back on October 2nd. Harvard astrophysicist Loeb, you might know him, he's been pretty vocal about looking for signs of alien technology. He requested those images. The response? Silence. Just nothing. And it gets weirder. China's Purple Mountain Observatory tracked this object intensively through August and early September. They were publishing regular data, keeping the scientific community updated. Then immediately after the Mars flyby, they stopped. Complete radio silence, their official reason, scheduling conflicts with lunar missions. The timing is, let's just say, curious, shall we? Now, I want to be crystal clear about something right up front. I'm not here to fuel paranoia or push some wild conspiracy theory. This isn't about aliens unless the data genuinely points that way. What I want to do is walk you through what we actually know, what we can measure, what we can verify, because even without those hidden images, what we can see defies comfortable explanation. Let me take you through what happened during perihelion, what changed, what didn't change, and what still makes absolutely no sense to the astronomers studying this thing. But first, we need to understand where this object came from, and I'm not talking about another star system in a general sense. I'm talking about something much stranger, something that honestly hurts my brain to think about. The data suggests 3I Atlas is 10 billion years old. Our entire solar system, only 4.6 billion years old. This object existed before our sun ignited, before Earth formed, before anything you can see in our cosmic neighborhood even came into being. It's not just visiting from another star, it's visiting from another era of the universe entirely. Think about that timeline for a second. Really think about it. When 3I Atlas formed, the universe was less than half its current age. The first generation of massive stars had lived and died. The Milky Way was still being shaped by violent mergers and collisions. The cosmic environment was completely different, and somewhere in that ancient cosmos, this object took shape. What kind of conditions create a comet that survives for 10 billion years? How does something remain intact through that much time? Through gravitational encounters with countless stars, through the radiation of multiple stellar environments, through the vast, empty, hostile darkness of interstellar space for billions of years? The answer honestly should be, it doesn't. Natural comets are fragile things. They're basically dirty snowballs held together by weak forces. Time destroys them. Radiation erodes them. Gravitational perturbations from passing stars tear them apart. They're temporary objects on cosmic timescales. Yet here's 3I ATLAS, ancient beyond measure, intact, functional, and actively venting gas as if it were freshly formed yesterday. That alone should be weird enough, but we're just getting started. Let's talk about what makes this object truly bizarre. Not speculation, not theories, just the raw, peer-reviewed, published scientific data. The facts that professional astronomers with PhDs and decades of experience can't explain away with comfortable answers. 1. Its trajectory. 3I ATLAS isn't just randomly passing through our solar system at some arbitrary angle. Its path aligns with the ecliptic plane, that's the flat disk where all our planets orbit, to within 5 degrees. The statistical probability of this happening by pure chance, 0.2%, that's 1 in 500. Now you could argue that's unlikely but not impossible, fair enough. But it gets weirder. Its arrival time was perfectly calibrated to bring it within tens of millions of kilometers of Mars, Venus, and Jupiter, 3 planets, and to position it directly behind the Sun, completely invisible from Earth during its closest approach. The probability of all those alignments occurring naturally, 5 in 100,000. You could still argue coincidence, right? The universe is vast. Strange things happen. I mean, someone wins the lottery every week, and those odds are terrible too. Okay, fair point. Let's keep going. Anomaly number 2, the Sunward Jet. Between July and August, multiple observatories, including the Hubble Space Telescope, which is not some amateur backyard setup, documented something unprecedented. 3I ATLAS was venting material directly toward the Sun, not away from it like every normal comet toward it. Now let me explain why this is a problem. Comets develop tails because solar radiation pressure pushes gas and dust away from the Sun. It's fundamental physics. The pressure of sunlight, the solar wind, all of it pushes material away from the heat source. That's why comet tails always point away from the Sun. Even when the comet is moving away, the tail always points away from the Sun. Always, except when it doesn't. This wasn't an optical illusion caused by viewing angle. Multiple telescopes from different positions in space confirmed it. This thing astronomers call an anti-tail, this sunward jet, persisted for weeks. And then, sometime in October, it just disappeared. The comet's plume shifted direction. Now it behaves normally, venting away from the Sun like it's supposed to. What kind of mechanism allows a comet to reverse the fundamental direction of its gas emission? What changed between August and October? What happened? Anomaly number 3, the composition. When astronomers analyzed the spectral signature of 3I ATLAS's gas cloud, basically they split the light into its component colors to see what elements are present. They found nickel, lots of nickel, 4 grams per second continuously venting into space. Now that's not unusual by itself. Some comets contain metal compounds, but here's the problem. There's almost no iron. The nickel to iron ratio is completely wrong. In natural cosmic objects, iron dominates. When stars forge heavy elements through fusion, they make iron and nickel together in very specific proportions. Nickel appears as a trace element, a small percentage. The ratio found in 3I ATLAS's plume, it matches industrial nickel alloys, human-made materials, not natural stellar chemistry. The probability of this ratio occurring naturally in a comet, less than 1%. And the nickel to cyanide ratio, another measurement they took, is orders of magnitude higher than any known comet, including Borisov, which is the other confirmed interstellar comet we've detected. The likelihood of that ratio occurring naturally, also less than 1%. 4. Water content. Normal comets are basically ice balls in space. Water dominates their composition. We're typically talking about 70 to 80% water by mass. That's what makes them comets. That's what makes them active. That's why they develop those beautiful tails when they get close to the Sun. The ice sublimates, turns directly from solid to gas, and creates that characteristic glow. 3I ATLAS, 4% water, 4%. It is venting water vapor. That's how we detected its activity in the first place. But the actual water content is absurdly low compared to every comet we've ever studied. What kind of comet barely contains water? That's like finding a snowball that's mostly made of something other than snow. 5. Extreme negative polarization. Okay, this one gets a bit technical, but stay with me. When light bounces off an object in space, it can become polarized. The light wave waves align in certain directions. Different materials polarize light in different ways, so we can use this as a diagnostic tool to figure out what something is made of. 3I Atlas exhibits a polarization signature that has never been seen before in any comet, not just unusual, not just on the high end of the range, I mean completely outside any known parameters, including Borisov, our other confirmed interstellar visitor. The measurement is so far outside the normal range that the statistical likelihood is, once again, less than 1%. 6. The WOW signal connection. Now, this is where things get really interesting, and I want to be careful here because this could be pure coincidence, but it's a hell of a coincidence. In 1977, the Big Ear radio telescope in Ohio detected a powerful narrowband radio signal from space. It lasted 72 seconds. The signal was so strong, so clearly artificial looking in its characteristics, that astronomer Jerry Amon wrote "Wow" in the margins of the data printout. That's why we call it the WOW signal. No one has ever found the source. No one has ever detected it again. It remains one of the most intriguing mysteries in SETI research. Here's the thing, 3I Atlas arrived from a direction in the sky that aligns with the WOW signal's origin point to within 9 degrees. The probability of that alignment, 0.6%. Now, could this be coincidence? Absolutely. Another dice roll in an infinite universe. The sky is big, things align by chance all the time. But when you start adding up coincidences, let me do some math for you. When you multiply all these individual probabilities together, the trajectory alignment, the arrival timing at multiple planets, the Sunward Jet, the nickel to iron ratio, the water content, the polarization signature, the WOW signal direction, you get a cumulative likelihood of less than 1 part in 10 quadrillion, 1 in 10 quadrillion. For context, the odds of winning the Powerball lottery are about 1 in 292 million. You would have to win the Powerball jackpot 34 million times in a row to match these odds, 34 million times. So either 3I Atlas is the luckiest coincidence in astronomical history, or something else is happening here. Now let's pump the brakes for a second. I need to be clear about something. Extraordinary claims require extraordinary evidence. The scientific method demands skepticism. It demands that we don't jump to conclusions just because something looks weird, and the vast majority of astronomers, we're talking about 90+% of the professional community, believe 3I Atlas is a natural object, a comet formed in another star system, ejected into interstellar space, now passing through our cosmic neighborhood by chance. And you know what? That's probably correct. Nature is incredibly creative. The universe contains phenomena we haven't even imagined yet. The absence of precedent doesn't equal impossibility. We've been studying comets for what? A few hundred years with primitive telescopes and maybe 70 years with modern instruments? That's a blink of an eye. We don't know everything. We probably don't know most things, but ignoring anomalies doesn't make them disappear, and what happened during perihelion made those anomalies more pronounced, not less. Let me show you what I mean. Space-based solar observatories captured something extraordinary during 3I Atlas's final approach to the Sun. Multiple instruments operating independently recorded the same phenomenon. The comet brightened at an exponential rate. Not gradual brightening, not the steady increase you'd expect from increased solar heating as it gets closer, not the predictable ramp-up of sublimation as volatile ices warm and vaporize. This was different. This was aggressive. This was unprecedented. The brightness increased inversely with distance to the power of 7.5. Let me translate that into plain language. As 3I Atlas got closer to the Sun, it didn't just get brighter in a linear way, like twice as close equals twice as bright. The relationship was exponential. The brightness curve was far steeper than any Oort cloud comet at similar distances. And remember, Oort cloud comets are fresh. They've spent billions of years in the deep freeze at the edge of our solar system, way out there beyond Neptune and Pluto. When they fall sunward for the first time, they're loaded with pristine volatiles, maximum ice content. They should outgas dramatically when they get near the Sun for the first time. 3I Atlas has 4% water content. It's ancient, it's depleted, it's been through who knows what over 10 billion years. It shouldn't be capable of dramatic outbursting. Yet there it was, blazing brighter with each passing hour. Stereo A, that's a solar observation spacecraft, captured images with 2 different instruments. Both the HI-1 heliospheric imager and the COR-2 coronagraph showed the comet developing an extended halo. This glow stretched 300,000 kilometers outward from the nucleus, 300,000 kilometers. That's almost the distance from Earth to the Moon. That's not a typical cometary coma. That's something else entirely. The SOHO spacecraft, which orbits at the Sun-Earth L1 Lagrange point, essentially hovering between the Earth and Sun, confirmed the observation with its LASCO coronagraph. Independent verification, multiple instruments, same result. And then there was GOES 19, the newest weather satellite, which happens to be equipped with a compact coronagraph called CCOR1. It resolved details the others missed. The structure of that 300,000 kilometer halo wasn't uniform. It showed layering, complexity, organization. But here's where things get truly strange, and this is the part that honestly keeps me up at night: the color. When astronomers analyzed the spectral data from LASCO and CCOR1, they found something that shouldn't be possible. The light coming from 3I-ATLAS was bluer than the sun. Pause on that. Really think about what that means, that when sunlight reflects off a comet, it should be the same color as the sun, maybe slightly reddened by dust particles, maybe slightly modified by the gases in the coma, but basically the same color. When a comet heats up and glows from thermal emission, when the surface gets hot enough to emit its own light rather than just reflecting sunlight, it should be red or infrared, cooler than the sun, not hotter. The surface temperature of 3I-ATLAS, even at perihelion, even at its closest approach to the sun, should be hundreds of degrees Kelvin colder than the sun's photosphere. The sun's surface temperature is about 5,800 Kelvin. That's what produces its yellowish white color. For 3I-ATLAS to appear bluer than the sun, its emission source would need to be hotter, significantly hotter. We're talking about temperatures that simply don't occur on natural comet surfaces. So where is the blue light coming from? The research paper published on October 28th by Zhang and Badams. These are professional astronomers. This is peer-reviewed work, states, and I quote, "The reason for 3I-ATLAS's rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar distances from the sun, remains unclear. They don't know. They're admitting they don't know. And regarding the blue color, they note it, suggests emission contributes a substantial fraction of the overall visible brightness." Emission, not reflection. Something on or inside 3I-ATLAS is generating light at high temperatures. What kind of natural process does that? What kind of comet contains an internal heat source hot enough to emit blue light? The authors don't offer an explanation because there isn't a comfortable one. Now you might be thinking, okay, couldn't this be fluorescent gas molecules? You know, solar ultraviolet radiation exciting gas molecules which then re-emit light at shorter wavelengths? And that's actually a good thought. Some cometary gases do fluoresce. Cyanide compounds, for example, can produce blue-green emission. But the scale is wrong. Fluorescence produces faint glows, subtle color shifts, not brightness that dominates the overall spectrum. And the observed blue shift was too pronounced for fluorescence alone to explain. We're talking about a significant portion of the comet's total light output being shifted to the blue end of the spectrum. You could argue for reflected light from an unusually bright, pristine, icy surface, like maybe it's covered in fresh, pure water ice that's really good at reflecting the bluer wavelengths of sunlight. But again, the scale doesn't work, and 3I-ATLAS is 10 billion years old. Its surface should be weathered, darkened by cosmic ray exposure over billions of years, covered in a layer of non-volatile material left behind as ices sublimate away. It should look dirty and dark, not mirror bright. The data doesn't fit the models. And when data doesn't fit models, you have three options. 1, the data is wrong. 2, the model is wrong. 3, something genuinely unexpected is happening. Let's assume the data is correct. Multiple independent instruments, different teams in different countries, all seeing the same thing. It's hard to dismiss that as measurement error. So either our understanding of cometary physics is fundamentally incomplete, which is entirely possible, or 3I-ATLAS is doing something comets aren't supposed to do, like operating an internal power source. Now, I'm not saying it is. I want to be really clear about that. I'm saying the observations would be consistent with that hypothesis. An engine generating heat, technology maintaining functionality over 10 billion years of operation, a craft designed to use solar flybys for energy replenishment. Pure speculation, absolutely, but let's follow the thought experiment for a moment. If you were sending a probe on an interstellar journey lasting billions of years, how would you design it? Think about the engineering challenges. You'd need extreme durability, materials that don't degrade over geological timescales. You'd need redundant systems, backups for your backups, and you'd need periodic energy replenishment because even the most efficient power source degrades over billions of years. Stars are convenient refueling stations. They're predictable, they're powerful. A close approach to a stellar photosphere dumps massive amounts of energy into any absorbing surface. If you had solar panels or some exotic energy collection system, a perihelion pass would be the perfect opportunity to recharge, absorb solar radiation, convert it to usable power, maybe even use the gravitational well for a trajectory adjustment if needed, but that's not what happened. According to NASA's automatic tracking data, 3I Atlas maintained its expected trajectory. No maneuver, no course correction. It came in, looped around, and continued outbound exactly where gravity predicted it should go. So if it is a probe, it's not interested in Earth, it's not altering course to investigate our planet, it's not deviating to get a closer look at us, it's just following its programmed route, passing through the solar system, gathering data perhaps, then continuing its eternal voyage through the galaxy, or much more likely it's just a really weird comet. But that blue light, though, that keeps nagging at me. And there's another detail that doesn't fit comfortably into the natural comet narrative: the timing of when things changed. Remember that Sunward Jet I mentioned earlier, that anti-tail that persisted for weeks during July and August, violating basic cometary physics? That jet disappeared sometime in October, right around the time 3I Atlas passed Mars, right before it went behind the sun. When it re-emerged on October 30th, the plume had normalized. Now it behaves like a standard comet tail, pointing away from the sun like it's supposed to. The anomaly corrected itself, or was corrected. Here's where we run into the information blackout, and honestly, this part frustrates me more than anything else. China's tracking data stopped after the Mars flyby. NASA hasn't released the high-resolution images from the Mars Reconnaissance Orbiter, which should have captured incredible detail when the comet passed just 30 million kilometers from Mars. What we have is before and after. Before, perihelion, anomalous behavior, sunward jet, strange composition. After perihelion, normalized tail, continued outgassing, maintained trajectory. What happened in between? According to Congresswoman Anna Paulina Luna, she's working to get those MRO images released. Avi Loeb has been increasingly vocal about the need for transparency. Radio observatories are now monitoring 3I Atlas for any electromagnetic emissions, following Loeb's public request to search for artificial signals. So far, nothing. No radio transmissions, no obvious signs of technology. Just a comet doing comet things, albeit in ways we've never quite seen before. The JUICE spacecraft, that's the Jupiter Icy Moons Explorer, currently en route to Jupiter, will observe 3I Atlas on November 2nd and again on November 25th. It's equipped with 5 instruments: a camera, a near-infrared imager, a UV spectrometer, a sub-millimeter wave instrument, and a sensor for detecting neutral atoms. JUICE is about half an astronomical unit away from the comet, that's 75 million kilometers. Too far for close-up imaging, unfortunately, but close enough for spectroscopy and compositional analysis. The data won't be downloaded until February 2026, though, because JUICE's position relative to Earth results in extremely slow data transmission rates. So we wait again. More gaps in the story. What we do know is that 3I Atlas survived perihelion intact. Some astronomers predicted it might fragment. Comets are fragile, and the thermal stress of a close solar pass can tear them apart, especially if they're loosely bound rubble piles held together by weak gravity. 3I Atlas didn't break, despite being heated to 770 watts per square meter at perihelion, despite the enormous tidal forces from the sun's gravity, despite being 10 billion years old and presumably weakened by eons of cosmic weathering. It held together. That tells us something about its internal structure. It's not a loosely bound rubble pile. It has structural integrity, strength, cohesion. Now, you could argue this is evidence of natural formation processes. Some comets are indeed monolithic, formed as single frozen bodies rather than being accreted from smaller pieces. That's perfectly normal. We've observed such comets before. Or you could note that 10 billion years is a hell of a long time for any natural structure to remain coherent. Micrometeorite bombardment alone should have eroded and fractured the surface over that time scale. Cosmic ray damage should have weakened the internal structure. Thermal cycling, heating and cooling over billions of years, should have created cracks and fissures. Yet here it is, intact, functional, venting gas like a fresh comet despite having 4% water content. Let me give you another another piece of the puzzle, something Avi Loeb discussed on the Joe Rogan podcast that really drives home the scale of what we're talking about here. The nickel emission, 4 grams per second continuously for months. Let's do the math. From discovery in July to perihelion in late October, that's roughly 4 months, about 120 days, about 10 million seconds. 4 grams per second times 10 million seconds equals 40 million grams. That's 40,000 kilograms, 40 metric tons of nickel vented into space. Now, 3I Atlas is estimated to be about 5 kilometers in diameter, with a total mass of roughly 30 billion kilograms, so 40 tons of nickel is about 1/millionth of its total mass. Doesn't sound like much, right? But remember, this is pure nickel we're talking about, not nickel-bearing minerals, not trace amounts embedded in rock. This is gaseous nickel, ionized, free in the plume. Where's it coming from? How is it being liberated from the surface or interior? Normal sublimation doesn't work. Nickel has a boiling point of almost 3,000 degrees Celsius. The surface of 3I Atlas, even at perihelion, doesn't reach temperatures high enough to vaporize metallic nickel. You need serious energy input, lots of it, either from an internal source or from some exotic surface chemistry we don't understand. And again, that nickel to iron ratio, it's cosmically wrong. The universe makes iron and nickel together in specific proportions through stellar nucleosynthesis. That's the fusion process inside stars that creates heavy elements. When a massive star explodes as a supernova, it scatters these elements into space in very specific ratios. Finding nickel without corresponding iron is like finding smoke without fire, unless the nickel isn't coming from natural ore, unless it's coming from manufactured components. Alloys, structural materials designed for specific properties, strength, corrosion resistance, durability over extreme timescales. I know how this sounds, I really do. We're pattern matching. We're seeing design where randomness might exist. It's a cognitive bias humans can't escape. We're wired by evolution to see intention behind unusual events. It's why we see faces in clouds and hear voices in white noise, but sometimes unusual events do have intention behind them. The challenge is distinguishing between the two, and right now, with missing data, hidden observations, and gaps in the timeline, we're operating with incomplete information, which brings me to the elephant in the room that I've been kind of dancing around. What if it is artificial? What would that actually mean? Let's think about scale for a moment. Our most ambitious spacecraft, SpaceX's Starship, the big shiny rocket that's supposed to take us to Mars, stands 120 meters tall. It can carry maybe 100 tons to low Earth orbit. It's the pinnacle of human rocket engineering right now. 3I Atlas is 5,000 meters across, maybe larger. Its mass is 30 billion kilograms. That's 300 million times heavier than Starship's payload capacity. If 3I Atlas were technological, its builders would have mastered capabilities so far beyond our current level that comparison becomes almost meaningless. We're talking about a civilization that could construct objects the size of mountains, accelerate them to interstellar velocities. We're talking tens of kilometers per second and keep them operational for 10 billion years. 10 billion years. Human civilization is roughly 10,000 years old. Recorded history spans maybe 5,000 years. Our entire species, Homo sapiens, has existed for only 300,000 years. 10 billion years ago, Earth didn't exist, the Sun didn't exist, the molecular cloud that would eventually collapse to form our solar system hadn't even begun to condense. Any civilization capable of building 3I Atlas would have emerged in a younger, stranger universe. They would have witnessed cosmic evolution on scales we can barely imagine. The formation of the first heavy elements, the assembly of early galaxies, the birth and death of multiple generations of stars. They would have solved problems we haven't even conceived of yet. Material science problems, energy problems, navigation problems, data storage problems. How do you build something that lasts 10 billion years? How do you store information that remains readable after geological ages? How do you maintain course over distances measured in light years? And if they sent probes, if they actually did this, why wouldn't those probes be designed to last, to observe, to gather data across geological timescales, to witness the birth of new solar systems, the emergence of planets, maybe even the development of life? Avi Loeb makes a compelling point about this. The discovery of technological artifacts from other civilizations would be the most profound revelation in human history. It would answer the fundamental question that has haunted us since we first looked up at the stars. Are we alone? But the implications extend way beyond philosophy. If interstellar probes exist, if they're common enough that one passes through our solar system every few decades, then the galaxy might be filled with them. Ancient observers quietly mapping the cosmos, reporting back to civilizations that may no longer exist, or maybe they still do. Think about that possibility for a second. Right now, as you're hearing these words, there might be billions of probes scattered throughout the Milky Way, silent witnesses to stellar birth and death, to planet formation, to the emergence of life. Some of them might be watching us right now. But let's pull back from speculation and return to what we know, what we can measure, what we can test. The International Asteroid Warning Network has initiated a formal observing campaign for 3I ATLAS. Starting November 27th and continuing through January 27th, 2026, multiple observatories around the world will coordinate observations. The campaign will include workshops on astrometry, that's the precise measurement of celestial positions and motions. Why? Because tracking potentially hazardous objects requires extreme accuracy, and 3I ATLAS, while not hazardous to Earth, serves as a perfect test case. It's large, it's bright enough to observe with professional equipment, and its interstellar trajectory provides unique challenges for tracking algorithms. But there's another reason for all this attention, an unstated one. If 3I ATLAS were to maneuver even slightly, we'd detect it. Any deviation from its gravitational trajectory would be immediately obvious to a coordinated network of observatories watching it 24/7. So far, nothing. The object continues on its predicted path, a pure ballistic motion, no thrust, no course corrections, just gravity doing its thing. That's actually pretty strong evidence against the artificial hypothesis, honestly. Probes maneuver, they adjust, they react to their environment. 3I ATLAS isn't doing any of that, or perhaps it already did. Perhaps the trajectory we're observing is the result of a maneuver performed centuries or millennia ago before we were even watching. Once you're on the right path through interstellar space, why waste energy on further corrections? Just coast, observe, record. The upcoming observations in December are going to be critical. On December 19th, 3I ATLAS reaches its closest approach to Earth, 269 million kilometers. That's almost twice the distance from Earth to the Sun, but it's the closest we'll get. Ground-based telescopes will have optimal viewing conditions. The Hubble Space Telescope will observe it. The James Webb Space Telescope, the most powerful telescope humanity has ever built, will observe it. Every major observatory on the planet will point their instruments at this object. They'll analyze its spectrum in unprecedented detail, map its surface features if possible, measure its rotation, look for any signs of internal structure, search for heat signatures that don't match expected solar heating patterns, and they'll listen. Radio telescopes around the world will monitor 3I ATLAS for electromagnetic emissions, any signal, any pattern, any deviation from random noise. If it's a probe, December might reveal it. If it's transmitting data back to its origin point, we might intercept that transmission. If it's using active sensors to scan Earth, radar or LiDAR pulses, we might detect them. But here's the uncomfortable possibility that I think we need to consider. What if it's designed not to be detected? What if it's been engineered to masquerade as a natural object? Passive observation, minimal emissions, camouflage that's indistinguishable from a real comet. How would you even test for that? How do you prove the absence of artificiality when the artificial could be designed to mimic the natural perfectly? You can't. Not definitively. You can only accumulate evidence, look for inconsistencies, find the places where the disguise fails. And 3I ATLAS has inconsistencies. We've counted at least 9 major anomalies that don't fit comfortable natural explanations. 9 data points that make professional astronomers uncomfortable. But 9 anomalies don't equal proof, they equal mystery, and mysteries can have mundane solutions. Let me offer you a natural explanation that actually accommodates most of these observations, because I think it's important to consider this seriously. Suppose 3I ATLAS isn't a typical comet, suppose it's something rarer, a fragment of a disrupted planet, a shard of a world that was torn apart by tidal forces during a close encounter with another star billions of years ago. This actually happens when a planet gets too close to a star or passes too close to another massive object. Tidal forces can rip it apart. The debris gets scattered into interstellar space. Planetary fragments would have different compositions than comets. They'd contain metals, core material, nickel-iron alloys from the planet's interior. If 3I ATLAS were such a fragment, the nickel emission suddenly makes sense. its venting material from deep inside exposed when the parent body shattered. The low water content? Explained. Planetary interiors are dry compared to comets. The water is all in the mantle and surface ice, not in the core. The structural integrity? Explained. Solid rock and metal, not fluffy ice and dust. The extreme age? Explained. Planets form early in a star system's history. A fragment could easily be 10 billion years old. What about the blue retri A continu light? Well, if the fragment contains radioactive isotopes, long-lived ones like uranium-238 or thorium-232, internal heat from radioactive decay could drive chemical reactions on the surface. Exotic chemistry that produces emission lines we don't typically see in comets. It's not impossible. The Sunward Jet? That could be related to localized venting from specific surface features. Geysers triggered by internal pressure, aimed in directions determined by the fragment's rotation and structural weaknesses. As the object rotates and heats unevenly, different vents become active, pointing in different directions. See, you can construct a natural narrative. It requires a pretty specific set of circumstances, sure, but those circumstances aren't impossible. Unlikely, perhaps, but not impossible. The question becomes, which is more likely? A rare natural object with multiple unusual properties, or artificial technology from an extinct civilization? Most scientists would say the natural explanation, however unlikely, is still more probable than the artificial one. And honestly, they're probably right, because we have zero confirmed examples of alien technology. We've never found anything artificial from another civilization. Not one single artifact in all our years of searching. But we have billions of examples of natural objects doing strange things. Pulsars sounded artificial when we first discovered them. Regular radio pulses, so precise we initially called them LGM1, for little green men. Turned out to be rotating neutron stars. Natural phenomena, fast radio bursts looked potentially artificial. Powerful, brief radio emissions from across the universe turned out to be natural, though we're still figuring out exactly what causes them. The prior probability matters here. Extraordinary claims require extraordinary evidence, and right now the evidence is circumstantial, suggestive, intriguing, but not definitive. So where does that leave us? We watch, we wait, we gather more data, and we prepare for both possibilities. If 3I Atlas is natural, understanding it will revolutionize our knowledge of planetary formation, stellar system dynamics, and interstellar object composition. It's a messenger from the ancient universe carrying information about conditions and processes that no longer exist in our modern cosmos. That alone makes it incredibly valuable scientifically. If 3I Atlas is artificial, well, everything changes. The Fermi paradox shifts from philosophical puzzle to solved mystery. We're not alone. We never were. The galaxy is populated, or was populated, by civilizations capable of reaching across the stars, and if they could do it, eventually, so can we. But here's what troubles me most about the artificial hypothesis, and this is something I keep coming back to. If 3I Atlas is a probe, it's not interested in us. It passed Mars within 30 million kilometers. That's close, really close on cosmic scales. Close enough to image the surface at high resolution, close enough to detect our rovers, our satellites, our entire infrastructure on Mars, close enough to see the tracks left by Curiosity and Perseverance, the landing sites, the communication arrays. If it wanted to investigate Earth, it could have. A small trajectory adjustment during the Mars flyby would have brought it much closer to our planet. Instead, it maintained course. It prioritized perihelion, its close approach to the Sun, over Earth examination. What kind of probe does that? What would be more interesting to an alien intelligence than a planet with technological civilization? Unless it already knew we were here, unless it had scanned us from a distance and determined we weren't worth a closer look. Maybe we're too primitive, maybe it's seen thousands of civilizations at our level and we're just not that interesting. Add us to the database and move on, or perhaps we weren't its mission priority, perhaps it was surveying the sun, not the planets, gathering stellar data, not biological data, measuring magnetic fields, solar wind composition, coronal mass ejections, things that tell you about stellar evolution and behavior. Or maybe, and this is pure speculation, science fiction territory, maybe it did investigate us, maybe it deployed smaller probes during the Mars flyby, subcraft too small to detect with current instruments, miniature observers now in orbit around Earth, watching, recording, waiting. I know, I know, that sounds like movie plot nonsense, but the universe has proven itself stranger than fiction repeatedly. Black holes exist, regions where gravity is so intense that space and time break down. Neutron stars exist, city-sized objects with more mass than the sun. Galaxies collide and merge over millions of years. Reality keeps surprising us with phenomena we couldn't have predicted. So why not this? Why not ancient probes traversing the galaxy? The answer might be coming. December will tell us more. February 2026, when JUICE's data downloads complete, will tell us even more. And the observations between now and then might reveal something completely unexpected, or they might confirm that 3I Atlas is exactly what it appears to be. A very old, very strange comet with properties we don't fully understand yet. But either way, we've learned something profound. The universe delivers mysteries to our doorstep, objects from beyond our solar system, carrying signatures of alien environments, reminding us that the cosmos is vast and our understanding is incomplete. Whether 3I Atlas is natural or artificial, it's teaching us, it's forcing us to question assumptions, to push the boundaries of what we think is possible, to refine our models and improve our instruments. And maybe that's the real value here. Not the answer, but the question, not the certainty, but the wonder. Because that's what drives science forward. That's what propels humanity to explore the possibility that something extraordinary might be real, that the universe might be stranger, more populated, more alive than we dared imagine. So we point our telescopes, we collect photons from objects 10 billion years old. We analyze spectra, we measure velocities, we build models and test hypotheses. And sometimes, just sometimes, the data refuses to fit our comfortable boxes. That's when things get interesting. Right now, as of late October 2025, 3I Atlas is moving away from the sun at about 210,000 kilometers per hour. Every hour it travels farther from the warmth that briefly illuminated it. Every day it gets colder, darker, more distant. It's currently within the orbit of Mars, but that won't last long. By mid-November, it will cross Mars's orbital path and continue outward. By December, it will be approaching the outer edge of the asteroid belt. By the end of 2026, it will pass Jupiter's orbit and begin the long journey back to interstellar space, and we'll be watching every moment of that departure. The viewing conditions are actually improving for Earth-based observers. During perihelion, 3I Atlas was lost in the sun's glare, observable only by specialized space-based coronagraphs. Now, as the angular separation between the comet and the sun increases, conventional telescopes can see it. Starting this past weekend, amateur astronomers with decent equipment have been able to spot 3I Atlas in the pre-dawn sky. It appears near Venus, rising before the sun, not bright enough to see with the naked eye, but visible through telescopes. A fuzzy patch of light, a visitor from another star system, close enough to photograph from your backyard. That's actually remarkable when you think about it. How many people throughout human history have looked at the stars and wondered what lies beyond? How many civilizations dreamed of touching something from another world? And now you can point a telescope at 3I Atlas and observe directly an object that formed in another stellar system. You're collecting photons that bounced off material created under alien conditions. You're witnessing in real time a fragment of a different cosmic environment. Professional observatories are going all in on this. The European Southern Observatory, with its array of massive telescopes in Chile, will track 3I Atlas throughout November and December. The Keck Observatory in Hawaii, those are some of the largest optical telescopes on Earth, will observe it. The Very Large Telescope will observe it. Subaru, Gemini, Magellan, every major facility will contribute data. They're looking for specific signatures, changes in brightness that might indicate outgassing events, variations in the spectrum that could reveal compositional differences across the surface, polarization patterns that might tell us about particle sizes in the coma, and they're looking for anything unusual, any deviation from expected behavior, any sign that 3I Atlas is more than it appears. The Hubble Space Telescope has already observed 3I Atlas multiple times. Back in July, Hubble captured that famous image showing the Sunward Jet. That single photograph revealed the anti-tail that sparked so much scientific debate. You can find that image online. It's genuinely striking, this bright, fuzzy object with a tail pointing the wrong direction. In December, Hubble will observe again, multiple sessions, multiple filters, maximum resolution. The images will show surface features, if any exist. They'll map the dust distribution in detail. They'll measure the rotation period with precision, and crucially, they'll look for changes, compare the December images to the July images. Has the surface altered in those 5 months? Have new vents opened up? Has the activity pattern shifted? Has something changed about this object during its journey through our solar system? The James Webb Space Telescope will join the observation campaign, and this is where things get really interesting. Webb operates in infrared. It detects heat rather than visible light. That's perfect for studying comets because it reveals things you can't see in optical wavelengths. Webb will map the temperature distribution across 3I Atlas's surface. It will identify hot spots and cold spots. Regions that are emitting more heat than solar radiation alone can explain if there's an internal heat source. If something inside this object is generating warmth, Webb will find it. Webb can detect temperature differences of just a few degrees across the surface. If part of this comet is warmer than it should be based on solar heating, we'll know. The Spheric Space Observatory already detected the carbon dioxide plume back in August. That observation showed the gas cloud extending outward, measuring its composition and velocity. The CO2 was moving at about 500 meters per second. That's pretty typical for cometary outgassing. In December, Spherex will observe again, looking for changes in the plume's characteristics. Has the CO2 production increased or decreased? Has the nickel emission continued or did it stop after perihelion? What about water vapor? Is it still present at that anomalously low 4% concentration? Or has it changed? These aren't trivial questions. They tell us about the object's interior. How deep do the volatiles extend? What's the internal structure? What's driving the outgassing? Is it purely solar heating or is something else contributing to the activity? And then there are the radio observations. Radio telescopes around the world are listening to 3I Atlas, the very large array in New Mexico. That's 27 radio dishes working together as one giant telescope. The facilities replacing Arecibo in Puerto Rico, the square-kilometer array prototype stations. Even SETI Institute instruments are pointing at this thing. They're scanning across the electromagnetic spectrum, looking for narrowband signals, the kind that would indicate artificial origin, broadband transmissions, repetitive patterns, anything that doesn't match natural emission. Avi Loeb specifically requested this after noting that wow signal connection. He argued publicly that ruling out artificial signals is essential. If 3I Atlas is transmitting, even weakly, we should be able to detect it at its current distance. We have the technology, we have the sensitivity, we just need to point our antennas and listen. So far, silence. Just the natural radio emission you'd expect from a comet's interaction with the solar wind. Charged particles from the sun interact with the comet's gas cloud, producing faint radio waves. That's normal, that's expected. No coherent signals, no patterns, no obvious technology. But absence of detection doesn't equal absence of signal, does it? Maybe it's transmitting on frequencies we're not monitoring. The electromagnetic spectrum is huge. We can't watch every frequency simultaneously. Maybe it's using directional beams aimed away from Earth back toward its origin point. Maybe it's not transmitting at all, operating in receive-only mode, passively collecting data without giving itself away. Or maybe it's just a comet and there's nothing to detect. That's still the most likely explanation. The Chinese space program presents an interesting wild card here. Despite going silent after the Mars flyby, China has significant resources in position. Their deep space network, the big radio dishes they use for lunar and Mars missions, can observe 3I Atlas if they choose to. Whether they're sharing that data is another question entirely. And this brings up an uncomfortable truth about modern astronomy. It's increasingly politicized. Nations compete for discovery priority. Data becomes strategic. Transparency suffers when national interests are at stake. If China detected something unusual during their September observations, would they release it publicly? Would they share it with the international scientific community? Or would they classify it, analyze it internally, and only release information after securing whatever advantage it might provide? Same question applies to the United States, honestly. Those Mars Reconnaissance Orbiter images, why haven't they been released yet? MRO routinely releases images within weeks of acquisition. These were taken on October 2nd. It's been a month. Where are they? Is it really just bureaucratic delays, scheduling conflicts, data processing backlogs, or is there a reason NASA wants to review them privately first? Congresswoman Luna's involvement suggests political pressure is mounting. Scientists want the data, the public wants the data, but institutions move slowly, especially when the implications might be significant, and make no mistake, the implications are significant. If those high-resolution images show anything anomalous, surface features that look artificial, geometric patterns, structures inconsistent with natural comet formation, the revelation would be historic, world-changing, the kind of thing that gets written into history books. but it would also be destabilizing. How do you tell the world that an alien probe just passed through the solar system? How do you manage the reaction, the questions, the fear and excitement and confusion that would follow? Maybe you don't release it all at once. Maybe you prepare the narrative, build the case slowly, wait until you have enough data to provide context, explanation, reassurance. Make sure you're absolutely certain before making such an extraordinary claim. Or maybe the images show nothing unusual at all and the delay is exactly what NASA claims. Scheduling conflicts, data processing backlogs, normal bureaucratic friction. Government agencies aren't exactly known for speed, we'll find out eventually. Data has a way of leaking. Someone on one of those teams will talk, an astronomer will share images at a conference, a researcher will post preliminary findings online. The truth, whatever it is, will emerge. But while we wait for that truth, the observations continue. Every telescope, every instrument, every wavelength, building the most comprehensive data set ever collected for an interstellar object. By the time 3I-ATLAS leaves the inner solar system, we'll know more about it than we know about most comets that formed in our own neighborhood. We'll have spectroscopy, photometry, polarimetry, radio data, thermal imaging, optical imaging, compositional analysis, terabytes of data, and from all that data, patterns will emerge, answers will crystallize, the anomalies will either resolve into natural explanations or persist as genuine mysteries. December 19th is the keystone date, closest approach to Earth, optimal viewing geometry, maximum instrument time allocated across every major observatory. If something's going to be revealed, that's when it happens. Imagine the scenario, December 20th, 2025, news breaks, Webb telescope detected anomalous heat signatures, or Hubble imaged geometric surface features, or radio telescopes picked up a signal. The headlines write themselves. The world stops. Confirmation that we're not alone, that intelligence exists beyond Earth, that the universe is populated. Every news network leads with it. Every website crashes. Social media explodes. Humanity collectively processes the most significant discovery in our history. Or imagine the alternative, December 20th, 2025, news breaks. All observations consistent with natural comet, anomalies explained by unusual but non-artificial processes. 3I-ATLAS is interesting, ancient, valuable for science, but not technological. The world shrugs, moves on, forgets about the interstellar visitor. Within a few weeks, life continues as normal. Which outcome would you prefer? Which outcome do you expect? I'll be honest with you, I don't know what I hope for. The romantic part of me wants 3I-ATLAS to be artificial, wants confirmation that we're part of a cosmic community, wants to know that intelligence is common in the universe, that we're not alone in this vast emptiness, that somewhere out there other minds have looked up at their night sky and wondered the same things we wonder. That would be beautiful, profound. It would give meaning to our existence in a way that nothing else could, but the rational part of me recognizes the complications. Contact, even passive contact through discovering an artifact, changes everything. Our place in the universe shifts overnight, our priorities reorganize. Questions about meaning and purpose in humanity's future acquire entirely new dimensions. And there's fear, too. If they're out there, why haven't they made contact? Where is everyone? If probes are common, if 3I-ATLAS is just one of many crisscrossing the galaxy, why the silence? Why hasn't anyone said hello? Maybe we're being observed, studied, cataloged, filed away in some vast database of emerging civilizations, waiting to see if we survive long enough to matter, waiting to see if we destroy ourselves with nuclear weapons or climate change or artificial intelligence before we reach technological maturity. That's kind of creepy when you think about it, being watched by something we can't see, being judged by criteria we don't understand, or maybe 3I-ATLAS is a relic, a ghost ship from a civilization that died billions of years ago, alone now, eternal, witnessing the universe on autopilot, reporting to masters that no longer exist. That's almost sadder than being alone, knowing they existed, knowing they built wonders, knowing they reached for the stars and succeeded, and knowing they're gone now, extinct for eons. All that remains are their probes, wandering the galaxy forever, silent monuments to vanished dreams. But these are emotional reactions, not scientific analysis. What matters is the data, the observations, the measurements, and those are coming in week by week, instrument by instrument. We're collecting the evidence that will answer the question. So let me make a prediction, and you can hold me to this. By February 2026, when JUICE's data download's complete, when the December observations are fully analyzed, when all the instruments have reported their findings, Jan will have a consensus, not proof necessarily, not absolute certainty, but a scientific consensus about what 3I-ATLAS most likely is. My guess? It's natural, a weird, ancient, compositionally unusual fragment of a disrupted planetary system, ejected into interstellar space billions of years ago when its parent world was torn apart by gravitational forces, now passing through our solar system by chance. That explanation fits most of the data. It's consistent with what we know about planetary formation and stellar dynamics. It doesn't require any exotic technology or alien intelligence. Occam's razor suggests it's the right answer. But I could be wrong. The universe has surprised us before, and wouldn't it be something if this time the surprise was intelligence? Let me zoom out for a moment. Away from 3I-ATLAS specifically, away from the detailed measurements and specific anomalies, let's look at the bigger context. We've now detected 3 confirmed interstellar objects passing through our solar system. Oumuamua in 2017, Borisov in 2019, 3I-ATLAS in 2025, 3 objects in 8 years. Statistical models suggest these detections represent a tiny fraction of the actual population. For every interstellar object we spot, hundreds or thousands pass through unnoticed. Too small, too dark, wrong trajectory, bad timing. The galaxy might be thick with interstellar debris, fragments of disrupted planetary systems, ejected comets, wandering asteroids, material scattered across the spiral arms, drifting between stars, occasionally falling into a solar system's gravity well. We're only now developing the technology to see them. Better telescopes, automated survey systems, sophisticated tracking algorithms that can identify moving objects against the background stars. As our detection capabilities improve, we'll find more, many more, and every one of them will be a time capsule, a sample of another star's environment, a piece of stellar history delivered to our doorstep. But here's the interesting thing, and this is what keeps people like Loeb asking uncomfortable questions. Oumuamua was strange, really strange, anomalous acceleration that couldn't be explained by standard cometary outgassing, an elongated shape, either cigar-shaped or pancake-shaped depending on interpretation, a bright surface inconsistent with typical asteroidal composition. It tumbled in a complex pattern. It didn't behave like anything we'd seen before. Borisov was normal, a textbook comet, water ice, carbon compounds, typical outgassing behavior, predictable trajectory, exactly what we expected an interstellar comet to look like. It was almost boring in its normality, which was actually reassuring. And now 3I-ATLAS, strange again, multiple anomalies, behaviors that don't fit comfortable models. 2 out of 3 interstellar visitors have been weird. That's either incredibly bad luck in our sampling, or weirdness is more common than we assumed. If weirdness is common, why? What makes interstellar objects different from solar system objects? Is it the environments they formed in, the processes that ejected them, the effects of traveling through interstellar space for millions or billions of years? Or is it something else? Could some fraction of interstellar objects be artificial? Not all of them, not even most of them, but some, a small percentage. Probes mixed in with the natural debris. If civilizations arise commonly throughout the galaxy, and we have no reason to think they don't, given that life emerged pretty quickly on Earth, and if those civilizations build probes to explore their stellar neighborhood, then over billions of years, the cumulative number of probes would be enormous. Think about it. One civilization sends out 10,000 probes over their existence. Those probes travel for millions of years, mapping nearby stars, gathering data. That civilization eventually dies out. Species go extinct, disasters happen, civilizations collapse, but the probes continue. They're machines. They don't care that their makers are gone. Another civilization arises somewhere else. They send out their probes, tens of thousands more. They die out too. Eventually, probes keep going. Over galactic history, millions of civilizations could have existed and vanished, each one potentially contributing probes to the interstellar environment. By now, ancient probes might outnumber natural interstellar objects in some regions, or at least represent a measurable fraction. This is the hypothesis Avi Loeb keeps returning to, not because he's committed to it being true, he's not, he's a scientist, but because it's testable. You can look for signatures, you can analyze anomalies, you can accumulate evidence that either supports or contradicts the possibility. And if even one interstellar object turns out to be artificial, everything changes, the Fermi paradox collapses. The great filter becomes less terrifying because at least one civilization survived long enough to build interstellar probes and scatter them across the galaxy. We're not necessarily alone, we're not necessarily doomed to destroy ourselves before we reach the stars. The universe has proven that intelligence can emerge, develop technology, and reach for the stars. That's worth investigating. That's worth the telescope time, the analysis effort, the scientific scrutiny, because the payoff, if positive, is incalculable. But even if 3I Atlas is natural, its value is immense. We're learning about planetary formation in other stellar systems. We're studying material that experience different chemical processes, different thermal histories, different evolutionary pathways than anything in our solar system. Every measurement refines our models, every spectrum adds data points, every observation teaches us something about the diversity of cosmic environments. And that knowledge is practical. Understanding how planetary systems form and evolve helps us predict which exoplanets might harbor life. Understanding cometary compositions helps us trace the origin of Earth's water and organic compounds, the building blocks that made life possible here. Understanding interstellar dynamics helps us map the galaxy's structure and history. Science builds incrementally, brick by brick, observation by observation. 3I Atlas is one more brick in that edifice. Unusual, yes, anomalous, certainly, but still part of the larger construction of human knowledge. So what should you take away from this whole story? What's the message here? First, pay attention to the anomalies. When data doesn't fit expectations, that's where discovery happens. That's where our models get refined or replaced. Easy answers are satisfying, but nature doesn't care about our comfort. The universe has no obligation to make sense to us. Second, remain skeptical but open. Extraordinary claims require extraordinary evidence. That's a fundamental principle of science, and it's a good one. But evidence can be extraordinary if you collect enough of it. Don't dismiss possibilities just because they seem unlikely. Calculate probabilities, test hypotheses. Follow where the data leads, even if it leads somewhere uncomfortable. Third, the universe is stranger than we imagine. Black holes sounded like science fiction until we detected them. Exoplanets were theoretical speculation until we found thousands of them. Gravitational waves were mathematical predictions until LIGO heard them rippling through space-time. Reality keeps surprising us. What sounds impossible today might be textbook material tomorrow. Stay humble about what we think we know. And fourth, we're living through a golden age of astronomy. More telescopes, better instruments, faster data processing, international collaboration on an unprecedented scale. For the first time in human history, we can study interstellar objects in real time. We can track visitors from other star systems. We can analyze their composition, measure their properties, test hypotheses about their origin. Our grandparents couldn't do this. The technology didn't exist. Our ancestors couldn't even dream of this. The very concept of objects traveling between star systems was pure speculation until recently. But we can do it right now, today, and 3I Atlas is just the beginning. More interstellar objects are coming. Better detection systems are coming online. The Vera Rubin Observatory, when it starts operations, will discover dozens or hundreds of interstellar visitors every year. Within a decade, we might be tracking dozens of these objects simultaneously. Within a century, we might be sending our own probes to intercept and study them up close. To rendezvous with ancient travelers and examine them directly. The galaxy is opening to us, slowly, gradually, but inexorably. Every year, we see farther, understand more, discover wonders we couldn't have anticipated. So when 3I Atlas fades from view, disappearing back into the darkness between stars, it won't be the end, it'll be a chapter. One story in an expanding library of cosmic encounters. And maybe, just maybe, one of those encounters will be the one that changes everything, the one that proves we're not alone, the one that answers the oldest question humanity has ever asked. Are we the only intelligence in the universe? The answer might be coming, not today, not this year, but soon, within our lifetimes potentially. As we explore more, detect more, analyze more, the probability of discovering evidence of other civilizations increases. It's a numbers game. Keep searching long enough and eventually you find what you're looking for, or you prove it doesn't exist. And when that discovery happens, if it happens, I hope we're ready. Ready for the implications, ready for the questions, ready for the transformation of perspective that comes with knowing, truly knowing, that intelligence exists beyond Earth. But until then, we watch the skies, we point our telescopes, we collect data, we analyze, we debate, we wonder, because that's what humans do. We're curious creatures, we're explorers, we're builders of instruments that extend our senses across the cosmos. We're the species that looks at points of light in the night sky and asks, what's out there? 3I Atlas gave us a glimpse, a tantalizing, confusing, anomalous glimpse. Not enough to answer definitively, but enough to keep asking, and sometimes the questions matter more than the answers. The questions drive us forward, they push us to build better telescopes, develop smarter algorithms, collaborate across borders and disciplines. The questions remind us that we don't know everything, that the universe still holds secrets, that discovery is possible if we're willing to look, so look up. If you have access to a telescope, point it near Venus in the pre-dawn sky over the next few weeks, find that fuzzy patch of light, that visitor from another star, that 10 billion-year-old mystery. You'll be observing directly an object that formed before the sun existed. You'll be collecting photons that traveled across interstellar space. You'll be participating in a small way in one of the greatest scientific investigations of our time. And maybe as you watch that fuzzy patch drift across your field of view, you'll feel what I feel, a sense of connection to the cosmos, to the deep history of the universe, to the possibility that somewhere, somewhen, other minds have looked at the stars and wondered the same things we wonder. Are we alone? 3. iAtlas doesn't answer that question. Not yet. Maybe not ever, but it reminds us to keep asking, and as long as we keep asking, keep observing, keep analyzing, keep wondering, we're moving toward the answer, however long it takes, however many interstellar visitors we must study, however many anomalies we must investigate, the answer is out there somewhere waiting to be discovered, and the next fuzzy patch of light we spot in our telescopes, the next interstellar wanderer that drifts through our solar system, that might be the one that finally tells us the truth. So stay curious, stay skeptical, stay open, and keep watching the skies, because you never know what might be coming next.